Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Beier Lee of the De Montfort University from Leicester, United Kingdom, who will be presenting his paper on OFDM-based Ethernet transmission over copper twisted pair cables. Beier Lee received his Bachelor of Science degree in Electrical Engineering at Beijing Institute of Technology in China and Master's of Science degree from Technical University in Munich in Germany. He has worked as system engineer for xDSL networks and DSLAM architecture design with Infineon and algorithm research with Bell Labs Alcatel-Lucent. He is now a Ph.D. student at De Montfort University in the United Kingdom. Beier, we welcome you to present at today's IWCS webinar series event.
Hello, everyone. This is Beier Lee, and today my talk is about the OFDM-based Ethernet transmission over copper twisted pair cables. So it's about the next generation Ethernet over copper cables. This is the outline of today's talk. We have some introduction on the background and the challenge in the next generation base T, or the next generation Ethernet over copper cable. Then we compare the multi-carrier and single-carrier transmission schemes. Then we introduce how do we adopt the OFDM transmission scheme over the Cat7a cable, and the simulation result and the summary is given in the end of the talk. So we start with a few questions and answers. Why do we still use copper cable since we have been heard about the optical fibers a lot? The copper cable is very convenient in the practical deployment. It's plug and play, and the overall cost of the copper cable is much, much lower than the optical systems. And what do we use the copper cable for the future, and what is the application scenario for the next generation base T cables? We believe that most of the copper cables will be used in the data center, especially in the very short reach, like the top of the rack scenario, which means it's used to connect the servers in the same server rack to the router on the top of the rack. The technical goal of this research is about what can we do with the data rate. It's about 40G, or the proposed 2550G over the four twisted pair in about at least 30 meters, and always we want a lower power consumption. So in the past, there are a few very straightforward approaches to push forward the evolution of the Ethernet transmission. For the first one, we always want better cable. During the manufacture, we always want to use more insulation to prevent the signal leakage. Another approach is to use higher frequency to transmit the signal, which means we can use more bandwidth. And the other one is to use more complex transmission techniques, like higher order modulation or more powerful coding schemes to transmit more information in each symbol. So all these footsteps can be concluded in these two tables for the evolution of the cables and the Ethernet standards. For the cables, we can see that we have used much more frequency from 16 megahertz up to the 1600 megahertz of the Cat7a cable. And we have now more braiding and foil for the cable screening and pair shielding. And for the Ethernet standards itself, we use more higher order modulation schemes from the basic Manchester code up to the PAM16 with a THP precoding system. And also, because thanks to the expanding frequency, the symbol rate has also increased from the 10 megabaud to the 250 megabaud per second now. So when we finalize the standards of the 40G base T, we do face some bottlenecks. For example, if we want better cable, we don't have much space to further install more insulation material or use even thicker conductors. So we see only very minor improvement in the cable itself. Or do we go to higher frequency? This is restricted by the conductor material, the copper itself. If we go to even higher frequency, the channel is degraded rapidly. So we are actually transmitting on a worse channel. Or can we use more complex transmission schemes? Yes, but we will face the silicon challenge, how to design the low-cost, low-power chipset for the transceivers. So we need some insight about the cable channel condition. Then we use this CFD Studio, which is a full wavelength simulation, to simulate the a very short cable to see what exactly is the channel condition like for the short cable. This figure is the insertion loss of the 1 meter long Cat7 cable. The black curve on the bottom of the figure is the 30 meters long standard cable as specified in the ESO document. And the top green curves, they are the 1 meter long cable, and this insertion loss is much better than the 30 meters long cable. And the group of the curves in the middle, they are the insertion loss of the individual wires under the unbalanced mode, where each wire is excited by its own excitation source, and the outer shield is used as a common ground. We can see that this insertion loss is not so good as the balanced mode, but we do have more channels for the available for the transmission. This slide is about the crosstalk performance, or more specific is the far end crosstalk, the signal leakage from one transmitting side and received at the other end. Again, the 30 meters long standard cable has the lowest crosstalk due to the longer cable length, and the crosstalk signal is well fainted. The two red curves at the top, they are the crosstalk of the unbalanced transmission mode between the two wires in the same pair. It's obviously the strongest crosstalk we see in this figure. And the green curves in the middle, they are the balanced mode. So it's between the pairs of the 1 meter cable. So it's not so strong as the pair, as the wire-wise crosstalk, but it's still stronger than the 30 meter long cable. And the two blue curves, they are the crosstalk between the wires from the different pairs in the unbalanced transmission. So this crosstalk is relatively weaker than the balanced mode. So now we come to two very interesting observations. The first one is the frequency selectivity in the channel condition, which means the crosstalk and insertion loss, they are different on the different frequencies along for the cable. And the other one is that the short cable, they have very, very good insertion loss, but they also have very strong crosstalk. So the performance of the short cable is yet to be evaluated. It's not necessarily much better than the long cable. And the proposed OFDM scheme is a well-known tool against the frequency selectivity in the communication channels. And it has been widely used in different systems. For example, the wireline communication systems, like the xDSL systems, they use OFDM transmission to transmit over the twisted pair telephone cable network, and also the DOCSIS, which is the TV cable coaxial cable network. It also uses OFDM to transmit the high data rate communication. And also the wireless and mobile communications, the modern ones we are using every day, they are all OFDM based. And what is this OFDM exactly? So the full name is Orthogonal Frequency Division Multiplexing. It is a multi-carrier modulation scheme where the whole frequency range is divided into many subcarriers. Then each subcarrier is a narrowband communication channel. Then we have a set of parallel narrowband communication channels. And in contrast, the current Ethernet, they uses the single carrier modulation, which is the PAM modulation, which is only transmitted at the highest frequency available of the system. The advantage of the multi-carrier transmission is that we have a very low symbol rate, and this ensures the channel, the different subcarriers can be better utilized with its own capacity. The mathematical interpretation of the transmit signal of the OFDM modulation is written at the bottom of this page. This is a functional diagram of the OFDM transmission transceiver blocks. So the upper part is the transmitter, where we can see the data is firstly converted from serial to parallel data streams, and each data stream corresponds to a subcarrier, and each of the stream, they are mapped into a QM symbol, and these parallel symbols are fed into the inverse FFT. In this transforms the frequency domain signal into time domain signal, and the time domain signal are mapped into the carrier, and it goes through the actual physical channel, the copper wire. At the receiver side, from the like the lower part, it's first picked from the copper wire, then it's again sampled and fed into the FFT as a time domain signal. Then this, through the FFT it transforms the time domain signal into the frequency domain signal, and this parallel frequency domain QAM symbols are demapped and then converted from parallel to serial again. Then we have our desired or detected signal. If we use the OFDM scheme, how about these straightforward approaches? Do we still need a better cable? It's not necessarily we can just use the same symbol because we can transmit more data over the same channel condition. So this also answers the second straightforward approach. Do we need high frequency? No, we just because this OFDM scheme is much can adapt itself better to the frequency selectivity. And do we need more complex transmission schemes? And how about the silicon challenge? Yes, but if we still use the single carrier, the challenge for the single carrier modulation is that we need a really high-speed serial processor. And now for this one, we have the parallel but low symbol rate. What we need is a powerful processing for the low symbol rate parallel processing. So they are essentially the same challenge. Moreover, the Ethernet cable has 4 twisted pair cables, twisted pairs in the cable. So we can take the advantage of the multi-user diversity. So each user has its own direct channel, like the insertion loss and return loss, and they have different coupling levels with each other. So they may have all these 4 pairs. They have different channel conditions on the frequencies. Then we can allocate different amount of we can allocate different amount of transmit power to these frequencies and to the users to achieve the optimal power efficiency. The well-known water feeding principle is mathematically proven to be power optimal, and we have a very easy to use low complexity called iterative water feeding algorithm to allocate the transmit power to the different users on the different subcarriers. In this way, the performance in terms of data rate can be further improved. Now we come to the simulation part. What can we? Here we propose our experiment set of parameters to configure our OFDM transmission over the Ethernet twisted pair cable, and with the VDSL2 and the DOCSIS system as a reference. Obviously, we have a much wider frequency. The VDS2 uses only 30 megahertz, and DOCSIS uses only 122 megahertz, and now we are using 1600 megahertz. So we divide these 1600 megahertz into 8,000 subcarriers, and the size of each subcarrier is 200 kilohertz. And we calculate the bit loading of each subcarrier. The bit loading is how much information can we transmit in each symbol on the subcarrier. There's a small technical problem with the slides, but it's basically the same Shannon formula for all these communication systems. We calculate from the received signal power level, and with the return loss and the other background noise, also the crosstalk as the interference. Then we can calculate how much information we can transmit, in this subcarrier. The total data rate is calculated by the sum of all the bit loading over all the subcarriers and times the symbol rate of the system. The simulation result is presented in this table, and we have 2 factors as variables to consider for the simulation result. So first, we can consider whether the crosstalk, alien crosstalk, is included or not. Alien crosstalk is the crosstalk from the other external cables. And the other factor is the cyclic prefix. Cyclic prefix is a common practice to prevent inter-symbol interference in the OFDM systems. It occupies a certain amount of the total bandwidth, so it causes some performance loss. Usually, it uses up to 15% of the total bandwidth. First, we look at the case where no alien crosstalk is considered. the total channel capacity of the cable is 85 gigabits per second. It's considered as 100%, and the flat Ph.D., which means no water filling OFDM, can achieve 72%, and which is about 72 gigabits, which is 85% of the total channel capacity. And the iterative water filling can further improve the capacity by 4%. So this means the 70. If we physically implement a system, the 72 gigabits per second gives us a really big margin to realize a 40G transmission or 50. And even if we consider the cyclic prefix, we can still achieve 65 without iterative water filling, or 68 with iterative water filling. So this one could be, which means we should consider this OFDM as a candidate for the next generation Ethernet transmission. Or similar conclusion can be obtained from the scenario where the alien crosstalk is considered. Alien crosstalk causes performance loss in the channel capacity as more external interference, but actually the OFDM can reach higher percentage in this scenario, like the 82% with the flat Ph.D. or 89% of the iterative water filling. So, which means the OFDM is more crosstalk robust for the system. Now, to sum up, first of all, the OFDM is a considerable alternative for the next generation Ethernet-based T. And we also see the robustness of the OFDM against the crosstalk, and its very good adaptivity in this channel frequency selectivity. Also, from the simulation, we see that the iterative water filling can further improve the data rate performance by 3, 4, or even 5%. And in the future, we will still focus on the possibility of OFDM with better configuration to improve the performance, and maybe also apply the more advanced joint signal processing of all the 4 lanes together to apply the multiple in, multiple out MIMO OFDM technique in this to see what we can do with this cable. Okay, that will be all of my talk today, and thank you.
And thank you, Beier. At this time, we will ask as many questions from the attendees as time permits. Starting with the first question, does OFDM technology essentially eliminate negative transmission effects of alien crosstalk?
Let me see the negative effect of alien crosstalk. Let's answer this way. It improves the performance, but it cannot really eliminate the It cannot totally eliminate the alien crosstalk. But alien crosstalk is also a frequency selective interference, so which means it generates different amount of negative impact on different frequencies. So in this case, OFDM can do better than the existing single carrier modulation. So I think the answer is yes.
Okay. All right, the next question, and I'll remind attendees, if you have a question, please post your question as soon as you can. Next question is this. The buzz on the street is now about Category 8 performance, definition, and specifications. Will Cat 8 performance provide any conflicts, or will it further enhance OFDM transmission?
Yeah, this is a very interesting question. The Cat8 cable is coming, and it definitely will not conflict with the OFDM transmission. But the OFDM, the OFDM transmission can better utilize the root channel provided by the Cat8 cable than the current schemes for sure. So let's say OFDM will only work better with a Cat8 cable.
Okay, thank you for that response. And I'm allowing, that's as many questions as I've received. I'm allowing just another half a minute or a minute here to continue. Okay, that kind of wraps it up. Thank you very much, Beier, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Beier after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 Eastern USA time. Our next scheduled webinar event will be on Friday, August 19th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so they can join in and register as well. For over 60 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual conference will take place on Sunday, October 2nd through Wednesday, October 5th, 2016, in Providence, Rhode Island, USA. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.